Hi everybody, this is Mark Weitzman and welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. Today we will continue with the Schensted book, and we'll be talking about projection operators and justifying them. Previously we've just shown what they were, but we haven't really proved anything about them. Today we'll have a short 3-line proof explaining how they work and why they are the way they are. So, this is Group Theory in Physics, Schensted Part 2, Chapter 1, Frobenius Algebra, Video 3, on projection operators. And last video we did the regular representation decomposition of the group algebra A of G. And the group algebra can be written as the sum corresponding to the regular representation, the sum from k equal 1 to r. Remember, each k corresponds to a unique irreducible representation, and we can split them up into left ideals, L1k, L2k, all the way up to L lambda k, L. Lambda k is the dimension of the kth irreducible representation, and just to make sure you understand, two representations can have the same dimension, but we're just ordering them from 1 to r. So often a group will have like our favorite group, the hydroidal group, will have a one-dimensional irreducible representation. The trivial one, another one-dimensional irreducible representation, sort of the one where we assign -1 to some elements and 1 to others, and then a two-dimensional irreducible representation. And notice that per our previous theorems, 1 squared plus 1 squared plus 2 squared equals 6, which is the number of elements of the group. But there are two irreducible representations of dimension 1. So the Lik are independent, irreducible ideals corresponding to the irreducible rep gamma kg. Now, it's important to understand that the decomposition into, L1k plus L2k plus, let me rephrase that. The decomposition into L1k comma L2k L lambda k is not unique. We can mix these in different ways and still get, but the overall everything, the sum in parentheses, corresponding to a particular irreducible rep is unique. However, once a choice is made, we stick to it, and then our previous expansion coefficients of group elements into the ideals is unique. So previously we had something like, if we had a group element, we could write it as like A1 plus A2 plus dot 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 A lambda K. These are unique. Once we make a choice of ideals for a given irreducible rep. Okay. Now, so the question is, how do we construct the lambda K independent left ideals corresponding to a particular irreducible rep gamma K. And what Schensted does is she states the answer and then proves and verifies the result. So I'm just going to give the one answer. So let's just say A. And it's defined by rho K C prime is equal to the sum from J equal 1 to N gamma K AJ. So we're summing over the group elements. We're taking the representation that we were given. Oops, I'm sorry. Notice how the order is reversed on these subscripts. We reverse the order there. And this should be an inverse here, AJ. And this basically C goes 1, 2, dot, 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 lambda K with C prime fixed. So if you remember, and let me just put an asterisk here. Use this formula. And this formula, we can always use unitary representations if we want. That's one of the theorems that were established earlier, that we can always use a unitary representation. The unitary representation formula is just quite similar. Just uses the unitary properties of the matrix. Here we don't invert the indices, and we put a star on it. The star here is complex conjugate, and again multiplying by AJ, C equal 1 to 2. Now, these are just the projection operators that were introduced in addendum A. And for each C prime, we can construct a set of lambda K vectors. Call them vectors or basis elements. They're really just group algebra elements. Why are they group algebra elements? Because the AJ over here is a group element, and these are just numbers. So we're just summing group elements with various coefficients. That's exactly what the group algebra is. And we get a total, since C prime, for each C prime we get lambda k, and then we have lambda k values of C prime. So we get a total of lambda k squared vectors. And if we sum over all k, we get lambda 1 squared plus lambda 2 squared plus dot 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 lambda k squared vectors, which we established in the previous lectures, just n. The order, the number of elements in the group, or you could think of it as the dimension of the the dimension of the group algebra. Okay, so now let's show that this works. Before I do that, let me just remark we can show using the orthogonality relations from lecture 3 of page 32. I'll write it down for you in case you probably don't remember that. Sum from j equal 1 to n gamma I AJ gamma k AJ u prime is equal to n over lambda I del I k del mu prime del mu prime. So using this, it's easy to show that the vectors or projection operators are independent. So what we have is a completeness. Since we get a total of n of them, we have a completeness relation for the group algebra. Essentially, we have n independent vectors, which are independent. They're independent, and they span the whole group algebra because there are n of them, and the group algebra is of dimension n. So, if we can just show that each of the lambda k ones are partners as we've used them before, then we'll have established what we want to show. So we want to show that, need to show that the lambda k vectors Rho 1 C prime K, Rho 2 C prime K, Rho lambda K C prime K, span a left ideal belonging to corresponding to gamma K. And previously what we said is, in other words, they form a set of partners. In the irreducible rep gamma K. Okay. So let's start. Let's multiply equation star on the left by AH. Okay. So this is a fixed element of the group algebra. We're going to show AH rho CC prime K is equal to the sum from J equal 1 to N gamma K AJ inverse. This is just a definition of the projection operator that we'd used before, except now we're multiplying it on the left by AH. These gammas over here are just numbers, so we can move the group element through them, and we get AH, AJ. Okay, so let's just put parentheses on this. When you sum from J equal 1 to N of the product AH, AJ goes over all the group elements. That's just the rearrangement lemma that's been discussed earlier in the course. So we can set AP equal to AH, AJ. Now this implies that AJ is equal to AH inverse AP, just multiplying on the left by AH inverse. And now we can take the inverse of the element. So we get AJ inverse is equal to AH inverse AP inverse, and then remembering the rules and groups for doing inverses, it's just AP inverse AH inverse inverse, which is AH. Okay, so we're going to use that. So now we get AH rho K CC prime is equal to the sum. Now we're not summing over J anymore, we're summing over P. For each J we'll get a unique P, so we're going to sum from P equal 1 to N gamma K AP inverse AH, because we need AJ inverse, and we established that over there. C prime C AP. Now we're going to use the representation properties. Remember that, our basic idea of a representation is gamma A, gamma B equals gamma AB, and these are matrices. So this is equal to the sum from p equal 1 to n, gamma k, AP inverse, C prime. I'm going to use another summation index, C double prime, so I should have put the sum over C double prime equal to 1 to lambda k. And that takes the first one, and then the second one is gamma k. Remember, this is just multiplication of two matrices. C double prime, C, AP. Okay, so we end up getting that AH rho C, C prime, K is equal to, now we can invert the order of the summation. The sum of C double prime, gamma K, I'm going to move this over here, AH, C double prime C, and now we're going to get gamma K AP inverse. I'm going to get the sum from P equal 1 to N, AP inverse, C prime, C double prime, AP. Now this is just equal to, if you look at the definitions we have, so we have the sum over C double prime, gamma K, AH, C double prime C, rho K, C double prime C. So this is exactly, it's exactly what we want. This is how partners and vectors transform under group elements. You can go back to the beginning of the course and you'll see this definition where of representation. We take, C double prime. We always sum over this index and this index. And, I'm sorry, this should be, let me make sure I got all these indices right. Okay, so this is C prime over here. So I have C prime, okay. So this is rho K, C double prime, C prime. Okay. So C prime always goes along for the ride. C prime just goes along for the ride. Anyway, this is what we want to establish. And basically this says that the vectors, group elements, whatever you want to call them, transform as a set of partners in the irreducible rep gamma K as claimed. They span a left ideal since when you operate on them with a group element, an element of the group algebra, you get back into that left ideal. So, and they're irreducible since gamma K is irreducible. So that ends this video, and next we'll do we'll illustrate this with special symmetry functions. Because the projection operators are fairly abstract, and the symmetry functions are more concrete. So thank you very much. I'll see you next time.